Metamaterials are artificial structures made of periodic or quasi-periodic inclusions of metals and dielectrics whose electromagnetic or optical properties can be engineered or tailored. The dimension of these inclusions, or cells, are typically much smaller than the signal wavelength at the frequencies of interest. Thus, these periodic structures behave as effective or continuous media, and their properties depend on how they are structured rather than on the composition of their constitutive inclusions. According to this, it is possible to create metamaterials with electromagnetic properties not found among natural materials. This is the case of the so-called left-handed metamaterials, which simultaneously exhibit a negative effective permeability and permittivity, and hence a negative refractive index, something not present among any known natural medium. The negative refractive index of left-handed metamaterials means that at the interface between a conventional material and a left-handed material, light refracts unconventionally, bending backwards. This phenomenon, known as negative refraction, has opened the way to a new optics, where the focusing can be achieved with planar lens. Super-resolution, namely focusing with sub-wavelength resolution, is another property of these artificial materials. Left-handed materials also support backward waves, that is, waves propagating opposite to the direction of energy flow. The combination of backward and conventional forward waves in planar structures has opened the way to the synthesis of communication circuits and systems with superior performance. However, the greatest impact of metamaterials has been caused by their potential application to the development of invisible cloaks. By point-to-point controlling the characteristics of the materials, radiation can be guided, and it is possible to create cloaks to hide objects based on the guidance of the light along their walls, thus avoiding dispersion and absorption, and hence making the objects invisible. The properties of hypothetical substances exhibiting negative permeability and permittivity had already been studied by the Soviet scientist Viktor Veselago in 1968. In this study, Veselago predicted that negative refraction should occur at the interface between a conventional and a left-handed material. However, due to the lack of these materials in nature, the work of Veselago was considered as theoretical speculation for years. The scene changed in 1999 with a work by John Pendry and co-workers who proposed a non-magnetic resonant particle able to provide a negative effective permeability in a certain region of the microwave spectrum, the split-ring resonator, SRR. By combining split-ring resonators with metallic wires, these being able to provide a negative effect permittivity, David Smith and co-workers from the University of California, San Diego, made the first synthesis of a left-handed metamaterial in 2000. This seminal work by Smith represented the Big Bang of the nowadays known as metamaterial science and technology. After this work, many works were focused on the experimental demonstration of the predictions of Veselago. To cite some examples, negative refraction in 2 dimensions was demonstrated in 2001 by Smith et al., and several groups worldwide have been working in subdiffraction imaging. Apart, of course, from the great expectation generated by the possibility to implement invisible cloaks. Open challenges in metamaterial science and technology are the development of 3-dimensional isotropic broadband metamaterials able to operate in the visible region of the spectrum. To this end, efforts at both the concept level and technology level are required. Recent results achieved by various groups with significant technological capabilities, nanotechnology laboratories, are very promising. Some of the metamaterial concepts can be applied to the field of radio frequency and microwave engineering. Specifically, as long as metamaterials are made of small size inclusions, the design of RF and microwave components with small dimensions is possible. Many components and devices employed in communication terminals are based on transmission lines, and their dimensions scale with frequency, thus being large for certain applications. However, in the design of communication circuits and systems, conventional transmission lines can be replaced with artificial lines based on metamaterial inclusions, with the result of smaller size and higher performance. The higher achievable performance is due to the unique and controllable properties of metamaterial transmission lines. These artificial lines exhibit more degrees of freedom than conventional lines, and higher performance as well as novel functionalities can be obtained through the implementation of RF and microwave components by means of metamaterials. Compact device dimensions, broadband and multiband components, electrically small antennas, advanced filters and diplexers, reconfigurable devices, reflectors, etc. are some of the possibilities of the metamaterial-based approach to circuit design.
These kind of structures could be used in any system where radio frequency or microwave signals are involved. This is especially useful in systems where the dimensions are a critical aspect. We might think in the design of filters, diplexers, power dividers with small dimensions and high performance. This could be used in sectors like aeronautic, aerospatial, or communications. We might also think in the design of small antennas to be integrated in RFID systems, or also in the design of devices reconfigurable or multiband.
The Research Center in Metamaterials for Innovation in Electronic and Communication Technologies, CIMITEC, is one of the leading and pioneering centers in technology transfer to industry on the basis of metamaterial concepts. Created in 2006, CIMITEC has been partially funded by the Catalan government through CIDEM and by the Universitat Autònoma de Barcelona, to which it is ascribed. It also belongs to the Innovation Technology Network of CIDEM, the Catalan government, and is a partner of the Virtual Institute on Artificial Materials and Metamaterials, Metamorphose Virtual Institute, AISBL, recently launched by the European Union through the network of Excellent Metamorphose. The main mission of CIMITEC is to carry out research of excellence in the field of metamaterials with an eye towards developing novel RF and microwave components with smaller size and cost and higher performance, or devices exhibiting novel functionalities. The CIMITEC laboratory has facilities for the design, fabrication and characterization of RF and microwave components. It is equipped with a drilling machine with 100 microns resolution and with several network analyzers and other test equipments with measurement capability up to 50 GHz. It has also electromagnetic simulation tools necessary for the design of microwave and millimeter wave components.
Well, the main aim of CIMITEC is to become a reference center concerning research and development on the basis of the new technology called metamaterials. We want to collaborate with companies worldwide on the basis of this technology, and especially in the field of microwave and radio frequency engineering.